most of you are well aware of the notion of slope stability, that we still start with reminding the definition. So slope stability of the vector bundle. So let me set up the explain the setup. So we have a vector variety X, and we consider a vector bundle or more general reflexive sheaf on X, and we fix in general some ample line bundle or ample divisor, or a little bit more general, we fix a net. Okay, so then we have the notion of slope. Let me denote this by mu of E. And actually, I should write mu d of E because it depends on the choice of our divisor. What is this? It's the intersection number obtained from the first term class of E and our divisor to the power n-1, where n is actually the dimension of X. And we have to rescale by the rank of our vector bundle. Okay, and now,
sorry,
yeah,
use X smooth or integral?
I think for the purpose of the talk, you can assume it's smooth. Okay, now our vector bundle E is called stable or semi-stable, and we emphasize that this depends on D. Let me call it D stable or D semi-stable, respectively. If we have mu, so our slope for any subsheaf of strictly lower rank is less or equal than the slope of the original vector bundle. And so we allow equality in the case of semi-stability. So for all so subsheaves F in E, and we have to be a little bit careful. So either we want that they are strictly low rank, or we want them to be saturated. Okay, good. Let me start with very basic examples, but which will play a role in the remainder of the talk. So, first one is if we take the tangent bundle on projective space, then this is in fact stable. Okay, and I'm not going to give a proof. So there are many ways actually to prove this for this particular case. Let me just emphasize that in general, it's not so easy to show that something is stable, because you have to check all sub-objects. If something is not stable, it's usually much easier to show this. You just have to make a good guess of the sub-object. Okay, so in general, this is actually a problem to show such a statement. Okay, now we are coming to a not stable situation. So if, for simplicity, let me assume that E decomposes into two line bundles. And then it's a straightforward calculation that the slope of E is just the arithmetic mean of the two slopes. So what we see is that the slope of E can be at most the slope larger of the two slopes. Okay, so this means such a situation can never be stable. So this means this is E is not stable. And actually this easily generalizes, so for sums of arbitrary ranks, then you get here some weighted arithmetic mean, same argument. Okay, in particular, and this is going to be interesting for us, if I take the tangent bundle of P1 times P1, then this is not stable. Actually, it's semi-stable if you pick good polarization on P1 times P1, but for no polarization, it's going to be stable. Okay, so those are the main examples for the moment. And now the central definition for this talk is the following. So we say X has stable tangent bundle. If the tangent bundle is stable or is d-stable for at least one ample divisor. Okay. Move to the next. Yeah.
One quick question. If you define stability using movable parts,
Yeah.
would this notion change?
Good question. So it's, I mean, for this talk, I'm only in the setting of surfaces, so there is no difference. So I didn't think about it. I guess, yeah, I don't know. Probably yes. Yeah. Okay. Then and first one is the d-stability, I call it this way, is actually an open condition in the choice of my ample divisor. I mean, this is immediately from the definition, right? So there we have very strict inequality. So then, second observation is, if I'm in the setting which is going to be important for us, that we have a proper birational morphism from some x to from some x prime on some x. And let's assume we have some vector bundle p prime sitting on x prime. So then I can calculate, and some divisor d living on x. Then I can calculate two numbers. The first one is I can pull back my ample divisor, which is going to be still nav, and calculate the slope of my vector bundle. Or I can push forward the vector bundle and calculate the slope with respect to d, and those two numbers are actually equal, and this is just projection formula. Okay. then as a consequence of those two, we get the following in the same situation here of such a proper birational map morphism. If X has stable tangent bundle, so has X prime. So this is preserved under birational transformations, or under proper birational morphisms. Okay, why is this true? I mean, so let's assume we have some ample divisor downstairs which makes the tangent bundle stable on X. We can pull this back, and if there would be, and we use this as our polarization upstairs, and if there would be a destabilizing subsheaf, then this equation tells us that the push forward of this subsheaf would be a destabilizing subsheaf downstairs. And okay, so the only problem is we have only something nav, but we can perturb it a little bit to get something ample. So yeah, so what this tells us is one way to obtain a variety which has a tangent bundle is just take one where you already know you have stable tangent bundle and you blow ups on it. And somehow the motivating question for what I'm explaining in this talk is this the only way to obtain varieties having this property? And one, yeah.
But it doesn't work the other way, right?
No. Okay, and so there's one result which goes a little bit in this direction. So this was here on by Jena, Benjamin Univ, myself, saying the following: if we have X a smooth toric surface, then we have the following implication, and X having stable tangent bundle implies that there exists a proper birational morphism from X down to P2. Okay. So, I mean, one interpretation of this is exactly that whenever you have a smooth toric surface, the only way it can have stable tangent bundle is through this mechanism. Or if you want to put it in more sophisticated words, you could say the property of having stable tangent bundle is inherited from one of the minimal models of our guy. Okay. Is there a question?
I'm confused because some blobs of P2 are also blobs of P1 times P1.
Yeah.
So you're saying that these that have stable tangent bundle do not fall in the lattice. Is that what you're saying?
No, I'm saying that whenever you blow up any other minimal model, then and it turns out the guy has stable tangent bundle, then there must be a blow down also to P2. Yeah. So in particular, if you blow up Q1 times P1, then the first blow up already has a blow down to P2. Okay. And this is exactly what I wanted to say next. So, I mean, as you can tell by looking at the authors of this theorem, we probably used very much toric methods to prove this. And so really going going on the side of combinatorics, and I think the paper is nice and or even beautiful. But so the aim for today is to see a non-toric proof of this statement, and the idea is, I mean, to see if you want to generalize this, for example, to rational surfaces, you should de-torify the whole construction. Okay, so, and this is the aim for the thing. So we want to see different proofs. Okay, so some facts which go in the direction of the question. So if we start with smooth rational surface, then you always have, let me say, X is not itself the projected plane, then there exists always a proper birational morphism down to a closable surface. So this means down to the projectivized bundle of the form OP1 plus O K, which is called the K closable surface. And by construction, you can see it also comes with a map down to P1. And since we are on surfaces, this actually means there's a sequence of blow-ups which brings you on in points, which brings you from here to here. So then the next fact is, okay, so that's easy to see. I mean, P1 times P1 is actually covered by this because the zeroth closable surface is just P1. Then you could ask, what about F1? And F1 is a little bit special among all those because actually it comes with a morphism down to P2, it's just the blow up of P2 in one point. Okay, then the next now become the question. Consider. So if you blow up F0, then the result actually comes with a or is a blow up of F1. In particular, so you can get it from P2. Okay. So this is, if you want, the structure theorem of rational surfaces. And now I want to make a definition, and I don't have a good term for this. I call it degree, but it's very misleading. So if X is not P2, then we note by degree of X, the minimal K such that there exists a morphism from X down to Fk. This fine? Okay, now let's maybe use this notion of degree and let's look a little bit what happens to our statement, or what we can say about the of the statement in several cases for the degree. Let's start with degree 0. So what could happen in degree 0? We could have P1 times P1 itself, which just, we figured out this does not have stable tangent bundle. So the assumption of the implication is not fulfilled. So the implication is automatically. Second case is we could consider a blow up of P1 times P1. But then we learned this will automatically come with a morphism down to P2. So the conclusion of the implication is fulfilled. So the implication is and the same for F1 and blowups of F1, they all come with a morphism down to P2. So the conclusion of the implication is fulfilled. So the implication is true. So this means we have to consider only things starting from degree 2 and show that the statement there is true. And now I have the following claim. So for x with degree of x is at least 2, and remember such an x comes with a morphism down to our Hilbert surface, and actually the morphism, then we can compose it to a morphism down to P1, and we call this composition I. And the claim here is that if we have this and the fibers are chains of P1s, then X does not have stable tangent. Okay, so this would prove this claim. This would take care of the remaining cases, and we just have this additional condition here that the fibers have to have a special form, but this will be fulfilled for toric surfaces. So on toric surface, I mean, you only have chains. You don't have trees or curves. Okay. So if we could prove this claim, then we would be done at least for the toric surface. Yeah, for the toric. Okay, so our aim is now to prove this claim. And let me start with a lemma. I want to reformulate this claim a little bit. So that's the aim here. So the claim is this is, or the lemma is, this is equivalent to, wait. I have to add, so that's completely fine, but I want to add a sentence here. So which reads like more precisely. So the point is, if we want to show that we don't have stable tangent bundle, we need to find a destabilizing sub bundle. Okay, and this is also a little bit tricky. So one has to come up with a good guess and find some canonically given sub bundles in this situation. But the situation comes with a canonically given sub bundle, namely the relative tangent sheet, which sits inside the tangent sheet. And the first one, what one would try is to check whether this is more precisely. What I'm saying here is that X, the relative tangent bundle destabilizes, or tangent sheaf destabilizes. Okay, and this, so the latter statement is equivalent to the following. Namely that the following curve class, which I denote by delta, and which is 2 times the first chain class of the relative tangent bundle minus first term plus tangent bundle is effective. Is pseudo-effective. So it's a limit of effective class, which doesn't make a difference in us. Yeah. Okay. Okay, let's prove this. Okay, so I want to show that mu of the relative tangent bundle is strictly larger than mu of the original thing, the tangent bundle itself. So I want to prove this inequality. Let me analyze what we do get here. I mean, this is the first channel class. This guy times d in our setting, and we ask whether this is strictly larger than first channel class of x tangent bundle of x times d. Okay, but now I just rearrange, bring everything to the left. Sorry. Almost, but the tangent bundle has rank 2, and the relative tangent bundle has rank 1. And remember, so for calculating the slopes, we have to divide by the ranks. So here's actually divided by 2. So this means I multiply by 2 and bring everything to the left-hand side. What we get is d times 2 times C1 relative tangent sheet minus C1 tangent sheet. And this should be positive for every d and for every amplitude. And now this is actually tells us by ampleness that this is equivalent for this curve class to be pseudo-effective and non-zero. And non-zero, yes. Okay, thanks. Good. So we see that we have to somehow look at this curve class, and our aim is to show that this is indeed effective. Okay, and for this, I need to get my hands actually on those expressions. So I mean, the first Chern class of the tangent bundle is just minus the canonical divisor. So this is, but I have to think a little bit or need some results telling me what is actually the first Chern class of the relative tangent sheet. So let me state or give a statement here, which is not our statement, but one which I'm going to need. Okay, before I can do this, I need to introduce a little bit of notation. So remember, we considered the situation where our x comes with some morphism down to P1. And in the end, we are interested in the relative tangent sheet of this morphism. And so, in the calculation of the first Chern class of this relative tangent sheet, there will appear a ramification divisor. And I have to define what this ramification divisor is. Okay. So let's call this pi. Okay, so then what I can do, I can pull back a class of a point from downstairs. So some y. The result will be the sum over components of the fiber over y. Let me call this components zi. And there will be certain coefficients in front of those fiber components, namely the multiplicity of those components as scheme theoretic, in the scheme theoretic fiber. Okay. And now I say, I define the number Rzi to be this coefficient minus 1. And I define the divisor, which runs over all fiber components of that map. And I assign to all fiber components these numbers. Okay, and I call this on, it's not me calling this, but it's called the ramification divisor. Okay, now I can state the statement I need. And I don't know where it's coming from. I know it from a paper one. And the statement is the following, not the first part, it's just the first part of the theory I'm writing down now is just what I already told you. The first term class of the tangent bundle is minus the x. It's always true, but now we come to the interesting point. The relative tangent bundle of tangent C. What we get here is the relative anti-canonical divisor, but that's not the answer. So we need a correction term, and this is exactly this ramification. Okay. Okay, so our aim is now using this description of the first term class of the relative tangent bundle to actually show that the curve class which we want to be effective to be. Okay, so that's our next claim for suggesting that the degree of x is at least 2. So then we know we have the sequence of blow-ups down to the Hildenburg surface at K, and with the composition down to. And the claim is that, and what we wanted to show, namely that this curve cloud we are interested in is indeed effective and non-zero. Okay, and the idea for the proof here is to wait. I'm not writing it down because I don't want to erase, but remember we had a condition. So I'm only claiming this in the situation which we are interested in, namely in the situation that the fibers of this morphism pi are chains of P1s. Okay, so this was the precondition or the assumption in this claim. So I'm still assuming this. And the idea is to prove this by induction on the number of blocks, which I have to do. So induction on L. Okay, and let's start with the situation of L being equal to 0. So we just consider the Hilbert surface. And this gives me the opportunity to talk a little bit about the geometry of the Hilbert surface. So comes with the map down to P1. And Hilbert surface comes with a distinguished section, negative section, meaning S squared is equal to minus K. And there are many other sections. So this one is unique. There are many others. Those have self-intersection plus K, so minus K. Okay, and then we will be interested in the class of a fiber. We have our small s hanging around, and we have F, which stands just for any fiber. Okay, and we want now to show that our curve class here is effective. And for this, we have to unravel just this, what's written here, right? So we have to actually use this theorem, think about what's going to be the canonical divisor on our Hilbert surface, what's going to be R, and what's going to be the relative canonical divisor. Okay, so what we are interested in is 2 times. Okay, so I said the relative anti-canonical relative tangent bundle, the first Chern class of it is given by the relative anti-canonical divisor. But what is this? This is the anti-canonical divisor minus the anti-canonical divisor from downstairs. But this is just 2 times a point class. So what we get here is 2 times the class of a fiber. Okay, and then so this had a correction term, it was this ramification divisor, and then we subtract minus the anti-canonical divisor, so in other words, we add the canonical divisor. Okay, let me simplify the expression here. So 2 times the anti-canonical one plus 1 times the canonical one gives us minus kx minus 4 f plus 2 r. Oh, I should write. Okay. Let me continue in this way. Okay, so now we have to think about back into whatever algebraic geometry would be like. So we have to figure out what is the anti-canonical divisor in this situation. So this is going to be 2s plus 2 times 2 plus a times f. And okay, so we substitute. Okay, so what we get here is 2s plus k minus 2 times f plus r. And we observe, I mean, this is clearly non-zero and effective. This is, we don't know exactly what it is, but it is effective for sure. Actually, it's 0. And this one is effective by our assumption here, right? So this is indeed effective and not equal to 0. Okay, so we are done with the first step in our induction. What's the idea now? I mean, the idea now is to see how all the quantities or all the divisors which appear here in this formula. So minus kx and r and we want f, how they change when I'm doing a blow up. Right, so that's our aim now. I'm going from x to x prime, which is a blow up. And I check what happens to all the ingredients of this curve class. Okay, so we get minus kx prime is equal to the pullback of minus kx, and we have to subtract the exceptional divisor or the exceptional curve. Okay, so that's general fact. We're all fine with this. Now, I mean, so nothing happens to a fiber. I hope this is clear. So the interesting point is what happens to well. And this is the point where we really have to use the fact that we want to have a chain of curves in our fibers. So otherwise, R does not behave as we want to. So let me just tell you what this means. If you want to get a chain of P1s in our fiber, then, and here I'm lying a little bit, essentially the only blow up which is allowed is that in the intersection of two fiber components. Okay, and this will be the case I'm talking about. Okay, so we are blowing up the intersection of two components of a fiber, and we see what happens to all our quantities appearing in our curve class. Okay, so the question is, what happens to the ramification divisor here? Claim is this is the pullback of of the ramification divisor downstairs, and then we get plus E. Okay. Let me first remark that if this is true, then we are obviously done, because what does it tell us? Yeah, for our curve class we are interested in, we then obtain that delta x prime is the pullback of delta of x and plus E. But if this was effective, pulling back it keeps the thing being effective, and then we even add something, so everything should be fine. Okay, so let me just have a look why this is going to be true. And then we are essentially at the end the proof, but I have a few more remarks to do. Okay, so so why is this true? Let me check what is the coefficient of the pullback of R at the exceptional divisor E. I mean, this is just the coefficient of the ramification divisor downstairs at one of the components plus the coefficient of the other component. Remember, we were blowing up the intersection point of two fiber components. Okay, so this is the answer here. And now let's compare this with what is R prime at E. Remember how the coefficients of the ramification divisor were computed, right, we looked at the pullback of a point downstairs, and then we collected the coefficient there, and we have to subtract 1 at every place. So this means if we reverse this, what we get here is we get Zi1 and plus Zi1. And so this is now what we get when we pull back the point class from downstairs. But we don't want the coefficient of the pullback of the point class from downstairs, but we want this one minus 1. So we have to subtract 1. Okay, so this is, if we now compare, it is and this is what we claimed here. Okay, so I hope this is satisfying. Okay, so I'm making the little square here. So I'm claiming now we have showed what we were aiming for. So we see on Fk we have this is an effective class, and we somehow compared the pullback or compared the pullback of this effective class with delta prime, if you like, or delta of x prime, and we obtained that again it's going to be effective. So we have shown the effectivity of the curve class we are interested in, and this by lemma 1 so tells us that the tangent bundle, relative tangent bundle is easily. Okay. Are there questions? Okay, so then what does it tell us? I mean, it tells us first that our theorem for toric surfaces is still true, which is good. But it tells us a little bit more because it gives us the same result for slightly more general class of surfaces. Namely, yeah, for those which fulfill this condition here, right? So which have as fibers chains of curves. If you want, you can rephrase this. I mean, the surfaces which come up in this way are actually those which admit a C star action along the fibers of this map. So what I explained here was actually we allow as blow-ups only fixed points of the C star action, which acts fiber-wise in our structure of a P1 bundle. So you could rephrase this and say, okay, so the theorem which I formulated for toric varieties is actually true for variety for surfaces, smooth surfaces with a C star which acts fiber-wise. But what's about more general surfaces? So basically, that's just the point here, and the point is things go wrong. Okay, so but it's actually once we start to produce trees of rational curves instead of just chains, then we get here something which is not longer effective. Let me just sketch the example. Our whole picture. So this is S. We have a fiber. Okay, and then we do a blow up at this point. Okay, up to here everything is still nice. So we get a chain. We do this once more. So this was so this is the strict transform of the fiber. This was our third exception divisor. This is our second one. So up to this point, we actually did what I was supposed to do. But now we do a bad thing. We blow up a point on here. We do it a second time and a third time. So, I mean, we blow up a point which lies now in the middle of one exception divisor. And then on that exception divisor, we blow up another point. And on the new exception divisor, we blow up yet another point. So this is 3, 4, and 5. And actually, in this case, one can check the curve class we are interested in is not effective anymore, which can be turned around. So it follows our relative tangent sheaf does not destabilize. Okay. But this doesn't tell us that does not have a stable tangent bundle. It only tells us, okay, our guess of a good destabilizing subbundle does not work. But actually, because it's a rank 2 bundle, you can actually deduce from this that or that X has semi-stable. Okay, I'm not explaining exactly how it works, but so we seem to be quite close. So there's one polarization where we get semi-stability, at least one. But we still don't have stability. And now I'm coming back to the remark which I did at the very beginning of this talk. Namely, it's hard to show that something is stable. So what one could do, so how to show that X actually has stable tangent angle. Okay, and I can think of 2 ways to do this. Maybe there are more, but the first one is we rely on our crucial idea. So, namely, we want to obtain a birational proper morphism to something down to something which has stable tangent phi. Okay, so our setup tells us this is not possible if we stay in the smooth rational surfaces, because I have chosen my example exactly that there's no proper birational morphism down to P1, down to P2. So the only chance would be to blow down not -1 curves, but curves of higher negative self intersections against some singular surface and try to show of pk rank 1, let's say, and try to show that this has stable tangent sheaf. And we think this works. And the reason is why you want to end up in pk rank 1 is there's some machinery to show that something has a stable tangent bundle by Petanel, but only in the smooth case. So you would have to adapt what Petanel did for the singular case to show this. So, so first thing you could do is find proper birational morphism X down to something, we call it Y, which now is a singular. Of pk rank 1. Okay, and as I said, this seems to work. So we have an idea, maybe we have a proof. Okay, second, and this connects a little bit better to maybe the topic of this conference. So there's the combinatorics here. Second. So actually, this thing still has a C star action. So it doesn't have a fiber-wise C star action, but you can do all those blow-ups such that C star action is preserved. So, and this gives you some tools at your hand, namely, why is it relatively easy to check that the toric vector bundle is stable or not? The reason is you have a very good understanding of their subbundles, or at least of the subbundles you are interested in. So let me have a review of the toric case. So, so here in general, if you have a toric vector bundle, then subbundles, at least the ones you're interested in, they actually correspond to sub-vector spaces. In a particular fiber of this vector bundle. Let me say the fiber over any point of the dense torus. And if you can choose any, you can also choose the identity element of the torus. Okay, so essentially, what makes it easy to check stability for toric vector bundles is that you just have to consider all possible sub-vector spaces of a given vector space. So you have a problem essentially in linearity. Okay, and now we have something which is not toric anymore, but it has what's called the complexity 1 torus action. So here the max, we don't have one dense orbit, but the maximal orbits are parameterized by, and now here comes something which might be nice or horrible, depending on your point of view. So by stacky non-separated P1s. Yeah. Okay, so this is the nice part, this is the horrible part. So the objects look like this. Right, so you have multiple points in the sense of non-separatedness, and you have multiple or stacky points in the usual sense. And now the situation is similar. Now you can reduce everything to consider bundles, vector bundles on here, and you have to study all sub-bundles of those vector bundles, which live on such an object. So, and I was adding this because I'm very much interested whether there are any tools to study vector bundles on these guys. So I was trying to find out more about this. This would be interesting, I think, for many more applications, but I couldn't find anything. And I think it's a hard problem, actually. So I think the stackiness and also the non-separatedness, so destroy everything you could hope for, what was true for P1, right? So there's no splitting, forget it. So those things are not so easy to study, but I think still there should be a possibility to study vector fields. It's easier than a generic variety, let's say. So I hope something is known or some people work on this. So this is more question than a remark. Okay, so let me stop here.